For those of you that were very eager to try your understanding on some problems, Nick has kindly posted a number of problems. Feel free to work through a subset of them or all of them, and Nick is happy to go over them. More will be forthcoming also. All right. Any questions on logistics while we're at it? Okay. Also, if you want to discuss ideas for the project, you can sort of book an appointment with either Nick or I. We'll be happy to talk. Okay, so last time we finished, I guess, a long journey to try to prove a rather strong result where every language in n time t can be probabilistically checked via proofs of polynomial size, polynomial in t, a polylog number of queries, and the verifier running in time that was a polylogarithmic, so exponentially less than the size of the witness. And then we saw how, since you cannot literally use PCPs as part of an information threading protocol for reasons that actually have to do with lower bounds on communication complexity for interactive proofs, we saw how to use cryptography, informally, specifically the use of collision-resistant hash functions to construct a so-called succinct argument. Okay, it's a proof system that is merely computationally sound, where the communication and the verifier are sort of much faster than the computation that is being checked. Okay, so this week we're going to take a small sort of venture into hardness approximation, which is one of the other applications of probabilistic proofs. One being delegation computation, and the other being sort of proving hardness approximation results. So before we jump into sort of some technical statements, I should probably motivate a little what this means. Okay, so we'll start out with maybe 10-15 minutes of motivating. What does it mean to study this direction? Why do we care? Okay. All right, so the motivation is, yes, probably briefly touched upon in undergraduate algorithms courses, that we have this class P of problems that we can solve in deterministic polynomial time. And there's many problems there that we care about. For example, shortest paths. That's one of them. Multiplying matrices, maybe that's another. Maybe the mother mother of all problems, linear programming. That is sort of P complete. But we also have a bunch of other optimization problems that are NP hard. Okay, in particular, we have in NP all these NP complete problems that we believe to be not in P, so that's why I'm drawing the picture this way. Okay, and and if indeed this is the state of the world, we do not believe that there exists a deterministic polynomial time algorithm to solve any of these. In fact, because of the reductions between them, it suffices to find an efficient algorithm for any one of them to solve all of them. Okay. Now, NP complete problems include many problems of interest, like scheduling, constraint satisfaction. And why are these problems of interest? Because they show up in places we care about. Okay, and that's why we want to solve them. Okay, and proving that a problem is NP complete doesn't make the actual problem go away, right? You're still left with the scheduling task or the, sort of finding a witness for it is whatever you're trying to do, right? Proving that it's NP complete doesn't make the problem go away. So you have to somehow find ways to so-called cope with this NP hardness. Okay, and there could be many ways you could cope with it. One is you take your head and you stick it in the ground, right? And that's one way of coping it. There are other maybe more productive ways of coping with NP hardness. Okay, let me list some of them. One of them is you just put up with algorithms that are not efficient. Okay. So use algorithms that do solve the problem. So I'm going to keep using the term optimally because even though P and NP really are about decision problems, it's just more natural to think about optimization problems. You can turn optimization problem into a decision problem by asking, does there exist a solution that is bigger than such amount or smaller than such other amount? Okay. So one idea is to just say, look, we're going to use algorithms that do solve the problem optimally, but because of the situation, we will make sure that the non-polynomial running time, non-polynomial necessarily, right? Running time is not bad on small instances, right? Because at the end of the day, you care about the problem of interest because you have some problem at hand, and maybe the instance at hand is not huge, so maybe it's okay to put up with an algorithm that doesn't run in polynomial time. So just to give us a numerical example, say that you look at an algorithm that runs in 1.1 to the n, okay? Even if you plug in, say, 1.1 to the 200, so at least when I plugged it into the calculator, this is less than 200 million. And I hope you can appreciate that 200 million is, astronomically less than 2 to the 200, okay? So look, like this is an exponential running time. If your instances, fit into 100, maybe, 200 million cycles is actually not so bad, right? Actually, in a modern computer, in 1 second, you will get 1 billion cycles. So you can sort of play games of this sort where you try to figure out, how large are your instances, what running time you can deal with. But the point is that you're insisting here on optimality, okay? All right, that could be one way to do it. So another way you could do it, you can say, well, use algorithms that, again, do solve the problem optimally. Okay? But only work, so work could mean different things, on natural instances. Right? So before, we were insisting that this algorithm work on all inputs, kind of worst case inputs. But again, the problems of interest may have some structure. They may be drawn from some distribution. They may not be those bad instances. Like it suffices to have one bad instance to kill an algorithm, right? It could just run in polynomial time on literally all inputs of a certain size but one, right? Maybe you don't care about that one input, right? So by work here, I mean that they will output an optimal solution in polynomial time, and maybe on non-natural instances, they will either run a long time or will output things that are not optimal, okay? And this is a very natural direction, and the main sort of theoretical challenge is what on earth does natural mean? Obviously, you could say, well, just pick a random input, but really, like real world inputs to algorithms probably are not random, right? And so both of these people have studied. For example, algorithms that run algorithms of this sort are rather common when you study lattice cryptography, when you're sort of studying the complexity of sort of things like shortest vector problem, because they're connected to solving other computational problems. You can actually run them in the real world, even though they're not running in polynomial time. And this direction has also been studied in theoretical computer science. It goes under the sort of umbrella term of average case and complexity, and it's generally like very difficult because you have to balance mathematically pleasing and tractable definitions of natural with useful ones, right? And it's kind of unclear where you draw the line. So if the more useful a definition appears to be, potentially like it just becomes like a messy theory that it's unclear how to make progress. Okay, so a third approach, which is the one that pertains to the subject of today's lecture, is to relax this requirement on optimality that we have insisted upon in the first and the second item is to use polynomial time algorithms that on every input, notice that so far I have said polynomial time and every input, so the only thing left for me is to give up on optimality. Otherwise, what else can I do, right? So then every input output a solution that is provably close to optimal. Okay? Such algorithms are known as approximation algorithms. Why? Because they approximate the optimal solution. Okay, and the motivation for studying this one is that if you're interested in some optimization problem, you may have, for whatever application you have in mind, sort of a near optimal solution could actually be like a reasonable answer of solving a reasonable way of solving the problem. Okay, you can have this graceful degradation in performance. Okay. Okay, questions so far? Right, so far this should be like review of the first time you probably have seen NP completeness. There's usually this type of discussion around how do you deal with NP hardness. Okay, so so let's define a little bit more precisely what is an approximation algorithm. So let's say in a maximization problem, we are given an instance of the problem X, okay, in some space. And we must find a solution S. The solution S will be in some space determined by the instance. So think about so maybe X is a graph, right? And the space of possible solutions could be maybe all flows on the graph or maybe all paths on the graph, something that's sort of determined by the instance of optimal value. So we have this S is going to be argmax over S prime in S of X of the value so we have some way to score the value of a candidate solution depending on the instance and the solution at hand. Okay. Right. And to some extent, you can think about the maximization problem to be precisely determined by this function. So that kind of specifies the problem for you. So it's kind of the function carries with it the domains, right, of X and Sx. And so this is a maximization problem. The minimization problem is kind of you put a mean and you're asking about the minimum value. Okay, so that's the problem. We're going to say an algorithm, and we will always consider polynomial time algorithms. A polytime algo A has approximation ratio alpha, and it's going to be always greater than 1. For this problem, if for every x in the set of instances x, the value that the algorithm returns for the solution that returned by the algorithm. Okay, so I want to compare to the optimal one, right? So I'm going to have some optimal value of x, right? And so we're looking at the maximization problem, so we can't go higher than opt, right? And I would like this one to be kind of alpha close to this one. So what should I write? Yeah, great. So this should be at least, and then y over alpha rather than times alpha, because alpha is at least 1, right? So I need to say that I'm trying to push up the value of my answers, right? And I can't go above this one, but I'm going to say I can't, the guarantee is that I won't go below the optimum over alpha, okay? So this is the notion of an approximation algorithm where its approximation ratio, or sometimes called performance ratio, is alpha, okay? Okay, just here, for minimization problems, one usually keeps alpha greater than or equal to 1, and the expression that you write is that the value of x and ax is, in this case, at most alpha times optimum of x. Okay? So this is the change that you would make for optimization problems. The point is that typically the convention is that the approximation ratio is, some quantity is at least 1. All right. So, okay, so this notion, I mean, is rather natural, motivates the goal, which is design approximation algorithms, for problems of interest for small approximation ratio alpha, right? So to the extent that one is able to make progress in this general direction, one is able to, cope with NP hardness. Obviously, here we are targeting NP complete problems, right? This doesn't mean that it doesn't make sense to talk about approximation algorithms for tractable problems. You may want to approximate a tractable problem with even more resource-bounded, even more resource-constrained algorithms. But whatever. This is just like a very flexible notion. Right now, we're really talking about NP complete problems. And so this direction is actually rather it's not that recent. People started thinking about approximation algorithms already in the 70s. And over time, it became clear that the different optimization problems behave rather differently under approximation. Okay, so some examples. Let me just write. People have been doing this. People have been doing this since the 1970s, and some examples of the ranges of results that people have been able to achieve. So, for example, knapsack, which is an NP complete problem, has actually an alpha approximation algorithm for every constant alpha greater than or equal to 1. Is this good or bad? That's great, right? So it says you can get arbitrarily close to approximating, the optimum. Okay. Sorry, oopsie. Ooh, that's it would have been very good, right? Very constant greater than 1, right? So that's good, right? So it's kind of so good that you might even wonder if the fact that knapsack is NP complete has of any consequence, to the actual problems, right? But this is just knapsack. That it doesn't necessarily mean that all of NP complete problems have this behavior. In fact, for example, for vertex cover, we have a 2 approximation, but nothing better is known. Okay, or maybe something slightly better is known. Actually, no, nothing better is known.
Why is that? Every NP program can be reduced to this problem.
That's a good question, right? So we have reductions between these. Why can't we reduce other problems to knapsack and benefit from that one? So we'll see in a moment. So I want to first write down this, so the variety of a sample of results. And And the reason is that traditional NP-complete reductions, or rather, polynomial time reductions between NP-completed problems do not preserve approximation ratios. Okay, and I will explain in a moment why intuitively that's the case. And actually, we'll see it in maybe a very stark example. So it has a two-approximation algorithm. In fact, this two-approximation algorithm is a very simple one where you have a greedy approach via matchings. Set cover. It has an O log n approximation algorithm. Okay. Also the greedy, sort of stupid one, where you pick the biggest set, you throw out the points, and you pick the next biggest set. And another, maybe last example I will mention, I'll mention dependent set, where it has, yeah, I guess I'll write it like this, order of n approximation. So, so essentially, people started studying approximation algorithms for a variety of NP-complete problems, and they kind of get stuck at different. So the state of the art stops at different, qualitatively different points. You could say this is kind of the best case scenario. We can approximate it to any accuracy. This is saying you can approximate it to some constant, but it is not known how to do it before. I mean, beyond that. This one is even super constant, right? And this is a polynomial approximation, right? And it's kind of really puzzling in the sense that some of these problems are really tightly related. For example, vertex cover, independent set are duals of one another, right? Somehow, when you reason about the NP-completeness of one versus the other, they're really like right there, right? They're pretty much the same optimization problem, but not really, right? Under approximation. And so the reason is that okay, I will come back to intuition for why something like this is not ludicrous in a moment. Okay, but this is a state of affairs of some sample, and the point is like approximation algorithms vary in quality very much, and if you trust the skill of people that design algorithms, you might suspect that there's something happening here, that some of these barriers actually have reasons to exist. So this motivates a new goal, which is to prove necessity of these barriers conditional on P not equal NP, right? So you want to prove hardness of approximation results. So this means that you want to prove statements of the sort that if there is an alpha approximation algorithm for some problem, for a particular problem, then you want to say this, then P is equal to NP. Okay? So this is entirely analogous to just the general theory of NP-completeness, where you want to say, look, I don't know how to solve this NP-complete problem. Let me just tell you that if I did, then P equals NP. Okay? So here we're just sort of extending that paradigm to say that not only can I not solve a problem exactly unless P equals NP, I cannot even solve it approximately for some setting of, for some sort of interval of approximation algorithms, okay? So that's the kind of type of statements that one would like to prove. And so let me try to argue at high level, why proving statements of this sort kind of is qualitatively different than just proving NP-completeness results, okay? So problem, kind of not clear how to prove good hardness of approximation. So if you take a step back and then you look at the theory of NP-completeness, how does it work? You have some generic computation of a non-deterministic Turing machine, right? This is what this is the machine model that recognizes NP. And we take the computational generic non-deterministic Turing machine and we plug it in the Cook-Levin theorem. And we reduce this problem to a three-set formula, right? And then we apply a particular reduction to the problem that we care about, to the problem of interest. For example, any one of them. Now, the model of computation of a non-deterministic Turing machine is, you can think about it as rather fragile. So if I kind of open up the computation, I go in one step, and I just flip a bit somewhere in one of the tapes of the Turing machine, this bit flip could actually ultimately change the machine from accept to non-accept or from non-accept to accept. Okay, there's no kind of robustness in this computation. Okay, does that make sense? Now, so what? Well, the Cook-Levin reduction has these locality properties that, in the sense that the three-set formula that I get out of it is a collection of clauses that operate locally on the tableau of computation on a deterministic Turing machine, right? How do I get the three-set? Well, I unroll the computation, I look at each adjacent time steps, and I look at every window where the Turing machine's head could have been, and I produce kind of tiny clauses for each of these steps, right? And then I take a bag and I push them all inside, and that's my three-set instance here. So basically, what this is saying is that the type of three-set instances that encode within them NP completeness don't have gaps. Like satisfiability versus not satisfiability could be due to a very small fraction of clauses, okay? And then whenever we continue from three-set to problems of interest, we are again operating locally. We're saying, look, why is, I don't know, independent set NP complete? Because I can actually design a gadget that is going to kind of compute for me a particular clause in the three-set bag of clauses, right? I forgot the fact that there was a Turing machine behind it. Now I'm just operating locally. So it's like I have two steps in each location, or in each of these reductions where everything is local. So what this is saying is that if suddenly I'm interested in, is it the case or not that many clauses are satisfied? Is it the case or not that there are many violations of the independent set condition? I'm not getting any big gaps, so I can't prove that an algorithm cannot distinguish, say, all satisfiability and half satisfiability, right? I'm only getting this 1 over poly gaps, okay? So this is just high-level intuition, and it's supposed, this high-level intuition of sort of the way that reductions are local and starting from a fragile model of computation should tell you that really NP reductions are kind of, they don't really tell you too much about sort of approximation factors, okay? Now, conversely, if our goal is to prove hardness of approximation, then maybe what we should do is we should start from a model of computation that is more robust, okay? That where it is rejecting transcripts are very far from accepting transcripts, okay? And at a very high level, intuitively, this is where PCPs come in. Okay, so we're gonna, at high level, this is kind of where it comes up, okay? So I'll just, maybe right here to summarize intuitively. To prove strong results about hardness of approximation, we need to start from a machine model of NP where accepting computations are far from rejecting ones. And intuitively, this is what we've been doing for several weeks, right? We're taking sort of witnesses for non-deterministic computations. We're encoding them into transcripts of computation, right? Where if something went wrong, we can catch it with high probability with a small number of queries. Okay? So at a very high level, this is where of how PCPs come in. Okay? Now, I think this is sort of enough sort of motivation and high-level intuition. I think we can look at a concrete example. This we're going to look at actually independent set. As alternatively, you can think about click. This was one of the first connections that was established between PCPs and hardness of approximation. This one? Apple. No, rejecting ones. This is a period. What? We're accepting computations that are far from rejecting ones. Yeah, sorry about that. All right, questions? All right, so far, I mean, it's mostly like a high-level discussion, just, All right, so now we start to doing something a bit more precise. So we're going to look at independent set. And our first humble goal will be to merely prove that it is not approximable within any constant factor. Okay? This will already separate it from a vertex color. Okay? So kind of qualitatively, we already learned that they're very different. Okay, so let me remind you what is independent set. So, given a undirected graph and a subset of the vertices, we're going to say we say that a subset of the vertices is an independent set. I'll just write independent set as IS. If what? Does anybody remember what is an independent set? Yeah, I pick any two things inside here, and I don't get an edge, right? So one way to say it is that if you look at every A and B in the Cartesian product S squared, we have that AB is not in E. Okay, that's an independent set. And the optimization problem that we're interested in is the max independent set. The max independent set problem asks to find an independent set of maximum size. Okay. Now clearly this is well defined because the empty set is an independent set, and all vertices is all you can take. Okay, so there is a maximum. So one exists, and the maximum also exists. Okay. Now, so proving hardness of approximation for max independent set is tantamount to proving hardness of, we're going to be seeing gap problems, okay? So the input to the gap problem is you have G, and which is the undirected graph, and you have an integer k, and the output is going to be a yes or no. Yes, if there is an independent set of size at least k, and the output should be no if every independent set has size at most k over alpha. Okay, so proving hardness with approximation alpha okay, is tantamount to asking an algorithm to distinguish these two things. So why are we doing this? Because remember, the tools we're going to be using, PCPs, are about decision problems, okay? So now we're considering a decision problem that has within it sort of a challenge of distinguishing, two answers that are a factor of alpha apart. If we had an approximation algorithm that works within alpha, then we could distinguish these. Okay, if there is none, then we can't. Okay, so what we want to do is we want to prove that this problem is NP hard, where alpha, whenever alpha is any constant. Okay. Okay, so the lemma that we're going to prove is going to say that if NP is contained in PCP with completeness C, soundness S, log n randomness and log n queries, okay, then there is no C over S approximation algo for max independent set. Okay, does the statement make sense? So not what? Oh, I should write bigger. Yes, thank you. Wait, does this small statement make sense? Okay, so notice that both the completeness and soundness play a role. Okay, and an important aspect of this statement is that it actually sits outside what we have proved so far, because the number of queries is log n, and all we've seen so far in terms of polynomial size PCPs is polylog n. I think the best we've gotten is something like at least log squared. So that's something that currently is an example of a query complexity that we still have to achieve. Okay, so we're going to motivate, and actually later on we will also see how constant will give us even better. So let's look at an example of a corollary. So we're gonna, it's not an assumption, it's a fact that we'll prove, since NP is contained in PCP 1/1/2 O of log n, O of log n. Okay, so we've seen this statement with polylog n. Okay, we have yet to prove this, but I'm telling you this is true. What does this lemma tell us? Yeah, we learned that unconditionally there is no two approximation algo for, wait, unless P equals NP. It actually tells us a little bit more. So definitely two approximation algorithm. What else does it tell us?
You can't get any constant approximation?
Yeah, any constant, right? Because I can just repeat this one a constant number of times. I won't pay for it here. Okay, I'll just get something here. I'll get any constant. Okay, so I also get that there doesn't exist alpha approximation algo for max independent set for any constant greater than 1. Okay, so something to notice here is that somehow soundness is important. Okay, and we'll see it sort of more later. Okay, but let's first prove this lemma. Okay, and again, this statement is enough to tell us that independent set just doesn't behave like vertex cover. Okay. Okay. So let's prove the lemma now. Any ideas? So really the fact that, so we can somehow use this statement, right? So we can start out by saying, suppose L is a language and actually maybe let me parameterize it further because it will be clearer. Suppose L is a language in this, okay? So we now show that there exists a reduction R such that first, for every x, R of x is an undirected graph, let's call it G of x, of size poly n, which is the size of x, 2 to the r, 2 to the q. Okay? We're going to show a way to map an instance of the language L to an indirected graph that is basically polynomial in n with an exponential dependence in r and q. Now, eventually, r and q will be logarithmic, so the entire thing will be polynomial. Okay? And then this reduction sort of does good things when x is in L and x is not in L. When x is in L, G of x, we're going to say something, and then when x is not in L, then what do you think we should say? What properties of G of x we should talk about if we want to make this connection? Yeah, so G of x, so I want to talk about independent set, but what should be the two cases? Like we're going to have to prove something about this yes and no cases, right? So maybe by analogy there, we'll see that G of x has an independent set that is large. And in this case, large will mean at least c times 2 to the r. Okay? And in the other case, we're going to say that the G of x will have all independent sets of size at most, and it will be s times 2 to the r. And notice that the ratio of these two is precisely c over s, which is kind of what we're trying to target. Okay? So this is what we want to prove. Okay? Or rather, this is how we prove this lemma. So let's do that. It's actually not a, I mean, it's a rather cute and so simple reduction. I'm going to do it maybe here. Yeah. All right, so we're basically left to specify R, right? R is a algorithm that will run actually in poly n 2 to the r 2 to the q time. And it receives an instance of the language L, and it spits out a graph. Now, so far we haven't used the fact that L is in PCP CSRQ, right? So intuitively, at some point, we would like to say, hey, L has a PCP verifier V with these features, okay? So how can we use the PCP verifier V to write a graph where independent sets sort of are related to how the verifier behaves? So hint, like we just really like we're in the framework now of NP reductions again. We want to kind of write down some gadgets that sort of encode the verifier's acceptance. So what kind of graph should we draw? I think once I write it, it will be like a very natural graph to study. So, okay, we fixed an instance x, right? Now for this x, remember the reduction doesn't know whether x is in the language or not in the language. It has to do something, right? So for this particular x, for every randomness choice, there is a set of answers the verifier will accept. Okay? So let's think about this. For every randomness choice, let's call it row in 0, 1 to the r. So why 0, 1 to the r? Because the verifier uses r random bits. The PCP verifier accepts any string. Let's call this set a row in 0, 1 to the q. So think about it. I fix a particular random string. The PCP verifier, will make some queries and will get back some answers. How many answers? Well, q. Okay. Now, it could be that every single possible q tuple that comes back makes the verifier accept, or maybe some of them don't. Okay. So let a for accept, depending on row, be the specific subset of q tuples that can make the verifier accept. So what I mean is, like, we should think about is that we have v for the PCP. It has x and you fixed row, right? And here they're really not. I mean, you don't have, once you have fixed row, you don't have to write here an entire proof string because we know what questions he is going to make. So a row is a set of, or rather, kind of let me put a string here, I don't know, omega. So it will output 1 if and only if omega is in a row. Okay? Now again, when I write omega here, I don't mean like he has oracle access to omega. Omega are the answers to the specific questions that it will make under this random string. Okay? So A of row are the so-called accepting configurations, of the proof. Is it clear what the definition is? Okay. So here's the graph. It's actually very simple as a graph. We're gonna define G as follows. So V is just going to be all possible accepting configurations across all possible randomness strings. Right? So here you have upwards of 2 to the q tuples. Here we have upwards of 2 to the q tuples. Okay? But I'm distinguishing them. Okay? So these are sort of different vertex sets. Here's you can think about it. Here maybe there is, these are accepting configurations. Here maybe there is these. Here there's maybe these guys. And here there's maybe 4. Okay? And I'm just considering, this is the vertex set of the graph. Okay? Now the edge set is going to be that, remember, independent set, I have to pick things that don't share edges. So I can put edges to prevent me from taking things together that I don't want them to coexist. Right? So what edges should I put between these columns to help me make my choices consistently? I want to somehow pick eventually what I will want is I want to force an independent set on this graph to tell me about an overall accepting verifier. Okay? So let's say that I pick, let's consider maybe this guy and this guy, okay, for a moment. And let's say that right now they're candidates in my independent set, and I'm just trying to reason whether they should or should not be together in my independent set. Let's say that this configuration and this configuration don't share any locations, okay? Like they're answers to like very different locations in the proof. Like on row 1, the verifier asks all questions in the first half, And on row 2, the verifier asks all questions in the second half of the proof. Do I care like about these whatever values these two configurations have in the same independent set? I don't care. They're never going to clash, right? So whatever answers they give, they don't have to be consistent, right? So in this case, I am not going to put an edge between them because somehow for them to coexist in the same independent set, that's okay. Okay? So now let's reason about a different, let's say that they actually overlap, say in one location, and these two particular configurations actually agree on what to say on that location. Do I care? Not a problem for me, right? So they can coexist because those particular configurations overlap on a location and they answer the same thing. The one thing that I'm worried about is when two configurations overlap and they actually disagree on some location in the overlap. In such a case, I'm going to put an edge because it will never be the case that those two will be together in my independent set. Okay, so I want to prevent that. I put down an edge. Okay? So the edge set will say that I'm going to put an edge between any two inconsistent configurations. Okay? Across columns. Actually, I have a few more edges to add, but they're not important right now. We'll see in the proof why we need to add them in a moment. But this is kind of the main thing. Okay? So right now I've written down a graph, okay, where basically what I'm trying to do is I want to force any independent set to be consistent with a full proof. Okay? If I pick an independent set, if I pick something from here, something from here, something here, something from here, right? And it is an independent set, this is something I could in principle extend to a full proof. Okay? Yeah?
So when you say inconsistent configurations, is it the case that there is no way of combining one string from the one and another string from the other, putting them together such that the overlapping places agree, that the bits will actually agree? Or is it just that there must be something in that, one string?
No, I think it's a much simpler thing. So imagine that there is an underlying proof that we're querying, okay? So one set of queries could say, I'm going to look at these three, right? And another set of queries could just say, I'm going to look at these three, right? Now, because, and maybe this is like, for randomness row, and this is for randomness row prime, okay? Now, remember that for each randomness, I'm considering all possible configurations, okay? So there could be configurations between row and row prime that actually agree on these two locations. I don't put an edge between them. But if these agree on either this or that point, then I will put an edge between them because I don't want these two configurations to coexist in an independent set. Okay?
Do you mean the right way is the union of all these A's?
Yeah, it's the union. So like, you should think maybe like I should have like drawn like the graph to be bigger, but this is a vertex set. This vertex set is disjoint from it. This other vertex set is disjoint from all the others. So
I guess it looks like here the vertices as these A sets, but they should be.
No, so we don't have meta vertices. The vertices. Sorry, that was. Now I see this could have been confusing. The vertex set has size at most 2 to the r times 2 to the q, meaning that there will be a vertex for every possible random string and for every possible configuration for that random string. Okay, thank you for the clarification. Okay, so that's the graph we're going to build. Again, we're missing a couple of edges, but they're not very important right now. So let's try to prove what happens to this graph depending upon whether x is in L or x is not in L, okay? All right, I'll get rid of this. Okay, if x is in L, then we're going to claim that G has an independent set of size at least guesses? So let's say that X is in L. What do we know about the verifier? Right, so if X is in L, we know that the probability that V PCP X over rho, where rho is random, equals 1, is at least C. And over what? Well, a proof, right? So there exists a proof pi, right? So this is what completeness means. X is in L. L has a PCP verifier with completeness C and soundness S. We know that there is a string pi that will make the verifier accept with probability at least C. Okay, good. Now we lay out all these things, and we have put down all the edges, and we want to demonstrate there is an independent set that is large. Remember, this is what I wanted to show, right? How do I pick my independent set? First, I'm going to claim that G has an independent set of size at least C times 2 to the R, right? But now we need to argue this step, okay? How do I pick my independent set? So remember, I have 2 to the R columns, right? I want an independent set of size C times 2 to the R. C is a number between 0 and 1. So really, I should pick, it suffices to pick one choice out of a C fraction of the 2 to the R columns, right? That would be enough. I need the entire thing to be an independent set. So for example, let's look at the first column. The first thing I should think about is row 1 one of the 2 to the R string, one of the C fraction of the 2 to the R strings that makes the verifier accept or not. Let's say that the verifier in row 1, it rejects. By the way, rejects what? Yeah, it rejects X, but there's a pi, right, that we're trying to reason about. So right now, I have fixed in my head pi, okay? And I'm saying, if row 1 causes the verifier to reject pi, should I be looking here for one of the vertices that want to be part of my independent set? Yeah, probably not. I mean, maybe I will find something here that will help me, but I don't need to look at it. So maybe I go to the next one. Row 2 makes the verifier accept. Which of the configurations should I pick? Yeah. Yeah, whatever is induced by pi, right? So row 2 will say, please read, pi 1, pi 3, and pi 5, right? That will determine a configuration of length 3. I'll come here. Let's assume q equals 3, and pick that one, right? So for every column where the verifier accepts, I will pick the configuration induced by pi. Now, because I have at least 2 to the R times a C random strings where the verifier accepts, I will pick up a candidate independent set of size at least C times 2 to the R. And now I'm wondering, will it be really an independent set? Clearly, it will have size at least C times 2 to the R, right? But let me first say, pick independent set. So pick configuration in a row induced by row, and I do this for all rows, okay? And now I need to argue, could it be that there is an edge between any two configurations here, right? So I have a configuration in one column here, another configuration in another column. Both of them correspond to the verifier accepting. Do I expect to see an edge between them? No, right? Because I only put edges between inconsistent configurations. These are just projections of the same proof. So they must be consistent, okay? So I have, once again, if the way I've selected my independent set is that I go in every column where the randomness makes the verifier accept pi, and I select the configuration induced by pi. Okay? Because I have many strings where the verifier accepts, I will pick up many points, many configurations. And these configurations all form an independent set because they are pairwise consistent. Okay? Is it clear? All right. Now I want to say that if X is not in L, then G has no independent set of size greater than S times 2 to the R. Okay? Well, these kind of things are easier to do kind of by contradiction. Suppose that there exists an independent set of size greater than S2 to the R. Then I would like to argue that I can construct a proof that makes the verifier accept with probability greater than S, and that would be a contradiction to the soundness. Okay? So I have this independent set, so it must be somewhere here, right? Now clearly this is independent set between columns, so if I have, let's say that, sorry? Right, so these are the edges that I didn't talk about earlier. So my danger right now is that I have a budget of at least S times 2 to the R nodes, vertices, okay? What I want them to be is to be spread out across at least S times 2 to the R columns. But, kind of the adversary might choose an independent set where it actually tries to fit multiple vertices in the same column. That would be bad for me, okay? Because really to construct a mutually consistent proof that is really accepting, I need them to be spread out. So what I also have to do here, I have to add clicks on every column. Okay, I'm going to put a click here, a click here, click here, click here, to prevent multiple choices in the same column. This does not harm completeness, this part, because anyways we're picking one vertex per column, right? And we're using these edges just in the soundness, okay? So I'm going to add clicks on each column. Okay? Now with clicks on each column, I know that if there is an independent set of size at least S times 2 to the R, it means that I have a selection here, maybe a selection here, section here. I have at least S times 2 to the R configurations that are all pairwise consistent. These values will determine a subset of a proof, or maybe the entire proof. But if it's a subset of a proof, I extend it with zeros arbitrarily. Okay, and that will give rise to a proof that is highly accepting. Okay. All right, then sort of there is one vertex per a row, at most one vertex. There's at most one vertex per a row, and can set pi to be arbitrary extension of the union of configurations in the independent set. Okay, so I just take all the configurations, I kind of sort of put them together. They may have intersections or not, it doesn't matter, they're consistent. Okay, and then I extend arbitrarily. The resulting proof, pi, makes the PCP accept with probability greater than S, strictly greater than S, and that's a contradiction. Okay. Now notice that this kind of felt like rather standard NP reduction. So where's the magic? The magic is that kind of it's already behind us, right? We're assuming that we have a PCP that gives us this gap, right, between C and S. Okay. So once we have the PCP, then sort of we have sort of not necessarily smooth sailing, but smoother sailing. Okay. So kind of we already have the gap. We have a model computation that is not fragile. Okay, and given that, we did a further reduction to the problem of interest, in this case, independent set. And this particular construction tells us that the way that C and S influence the approximation ratio is specifically in this way, C over S. Okay? All right, so the reduction really is like not that difficult. In particular, if you look at, I don't know, the traditional reduction of NP completeness of independent set, that sort of very similar in nature, right? You're using these edges to ensure consistency, right? And you're kind of spreading out your selection of the vertices across clauses by using also edges. Okay, it's kind of very similar in spirit. It's also not that difficult. Okay. Okay, so this proves this one, and we already looked at the corollary that we get no to approximation, and in fact, by just naive error reduction by a constant number of repetitions, we get no constant approximation for any constant greater than 1. Okay? All right, questions? Some of you look, seems like I understood everything. Others look more puzzled. So are there some questions I can answer that can help? Yeah.
Confused on what the vertices are for this. Is it the combinations of, like, is the combinations of configurations for the exception? I'm so confused.
So one way to think about the vertices is, maybe I'll just write sort of how they're indexed. Okay, where will I write it? I'll maybe write it here. The vertices are a subset of 0, 1 to the R cross 0, 1 to the Q. You can think about them that the name of a vertex corresponds to a random string, comma, let's say A. Those are the answers to the Q queries that the verifier made on rho. Okay? So the vertices basically says consider all possible random strings and all possible answers you could have gotten to those Q queries. Okay? So does it answer the question on the vertices? Yep.
So A of rho contains multiple strings of like
Q, yes, yes.
So then shouldn't it be like A of rho is a subset of the set of like
Sorry, I meant only the accepting ones. Sorry, I misspoke there. I should say only the accepting ones. Yeah.
Yeah, but like when you say A of rho is a subset of 0, 1 to the Q, shouldn't it be like a set
okay.
of all strings?
Yeah, I mean, I was kind of hiding the row 1 index. Okay, so because yeah, so let me put it like this. A of rho is subset of, how about like this? So A of rho are all vertices whose first coordinate is rho, and then whose second coordinate is Q. Okay, and I'm only looking at the ones inside here that are accepting. So this way, when I kind of put them all together, I'm getting vertices where the first part of the name tells you the randomness, and the second part of the name is the accepting configuration. So this would be at least syntactically consistent.
So in the TCP, the answer to each query can only be 0 or 1.
So right now we are looking, when I don't specify the alphabet, we're looking at a 0, 1 alphabet. Okay.
And also for per column, two configurations in the same column should be inconstant. So we don't need use the union two sets. So that should be a clicks, right? Because when the randomness is the same, But you have two different strings.
Yes, for non-adaptive verifiers, that's the case. So that's a good point. So the question is, for non-adaptive verifiers, having fixed the randomness, the queries that you ask are literally the same, right? So the only way you may consider another configuration is when you flip one of the locations. So that automatically will make it inconsistent. So if you were thinking of inconsistency sort of in the most general sense, then you would already put a vertex between the two, okay? For adaptive verifiers, maybe that's not so much the case. And maybe that we should just, let's not think about that case. Good point. All right. All right. Definitely, have a look at this at home. Now, let's try to understand how do we go beyond, any constant factor approximation. The first thing that is worth asking is, suppose we did amplify a little bit more, okay? We wanted to push the soundness to be sub-constant, then that means that the number of repetitions that we do would be super constant. And that necessarily in this reduction would mean that the reduction that we runs in super polynomial time. That's not necessarily bad, right? As long as we're not running in exponential time, we might be able to say something meaningful, okay? So let's see how much we can actually milk out of this for like a super constant approximation, and how bad would the reduction be, okay? And then, next time we'll see actually how to improve that back to polynomial time. So let me do it maybe here. All right, so in general, we know that PCP, I'm going to fix the completeness to 1 just to sort of not run into issues about majority. 1s, RQ is contained in PCP 1/2 to the t times r, t times q, okay? So this is just plain repetition. Let's try to set t to be log n. Okay, let's see if we get anything interesting out of it. Now the graph will have size that is, let's give it a name, n, is 2 to the r plus q, okay, which is, tr plus tq, okay, and let's assume that, both of these are, order of log n. So let's say that r and q are log n. We get 2 to the log squared n, right? That's what we would get, because you have log n times log n and log n times log n. The infeasible ratio is going to be n, right? Because we have 1/2 to the log n, okay? That will give you 1 over n. 1 over n will give you n. Now, n in terms of capital N is what? Wait, there's an O here. So yeah, there is a square root somewhere, and then here kind of, I don't think I can do this on the fly, but you just check it. That's what you would get. Okay? So I think hopefully somebody can check me. How do you check this? You take log of both sides, right? And you square. Okay? All right. So what does it tell me? What does it tell us? it tells us that if we have an algorithm that runs in n to the order of log n time, and approximates max independent set to within. By the way, why is it n to the log n? Because we have the algorithm was running 2 to the r plus q, okay? And now the r plus q is tr and tq, so 2 to the log squared is n to the log n. To within 2 to the little o of log n, then no, I messed up, sorry. I want to start from, I need to juggle the big N and the small n. And so big N is attached to the graph, small n is attached to kind of basically 3SAT or the PCP. Let me try to step it. Okay, if we have an algorithm that runs in polytime on graphs of size n, capital N, and approximates to within 2 to the little o of capital log n square root, then, okay, now I got it. There is an n to the log n algorithm for solving 3SAT. Okay. All right. The point here is that we have an approximation that is super constant, okay, to the square root of log n, little o of square root of log n, okay? And remember, whenever we want to prove hardness approximation algorithms, we're always considering polynomial time algorithms. So we are reparameterizing to say capital N is now the problem size, because guess what? The output of our reduction produces a graph, and we're running an algorithm on that graph, okay? And it say that it runs in polynomial time, and it approximates it to within this super constant factor. Again, n is the size of the graph. Then, we want to say a conclusion. We want to say a conclusion that is unlikely, okay? Through this parameterization, the only conclusion that we can say is that it's not that p equals np, which would be tantamount to saying that there is a polynomial time algorithm for 3SAT. We're saying there is a quasi-polynomial time algorithm for some NP-complete problem, for example, 3SAT, okay? This is not as strong as the conclusion p equals np, but it's still an unlikely conclusion, okay? So this is actually where pretty much in the original paper that sort of made this connection, things stand, okay? And we'll see next time how to kind of get into the super constant region, okay, without having to pay for this relaxation, okay? But this was just basically communicating that you can still try to sort of milk something meaningful out of the reduction that we just saw without pretty much doing anything, okay? So at this point, I think we are at the end of lecture, so I'm not going to try to do this again. Just check the parameters at home, and then the main thing you need to keep in mind is that the parameter of the graph capital N is different than the parameter little n, okay, that we are setting here. All right. So next time will be our second and probably last for a while lecture on hardness approximation, and we'll see how to push forward this hardness approximation result for an independent set. Okay, and we'll see how to do it using a more efficient soundness error amplification than the naive one.